Well, our scatter plots describe the data, but as always, when we describe, we also infer to the population. So given the scatter plot and also given the sample correlation coefficient, let's generalize that sample correlation coefficient to the population by doing statistical inference. So what we want to do then is we want to realize that every time we have a descriptive statistics, we'll want to generalize to the population in some way, at least with the confidence interval, if not with the hypothesis test. So the question of interest is, how close is the sample statistic to the underlying population value? We always want to know the population value, but we're always stuck just with the sample statistic. So the question becomes, how close is it? We don't know for sure, but we can two forms of statistical inference, the hypothesis test. Here we assume the null hypothesis that the population correlation is 0. And then we want to, then the alternative hypothesis is that it's not 0. And then we have the confidence interval. And the confidence interval is the range of values that likely contain the true population correlation. Just like the confidence interval for the mean and everything else, here we're talking about the correlation. So the confidence interval estimates the value of the population correlation at whatever specified level of confidence, like 95% or 0.95. We don't know what the population correlation is, but it's estimated to be within this particular range, which is the confidence interval. So where do we get this information? We get it by running the scatterplot function in less-r or the correlation function in less-r, which will give us that information. Okay, now before we look at some of the underlying concepts here that correspond to the output from the less-r functions, we have to realize that the statistical inference requires the degrees of freedom, which is the sample size minus the number of sample statistics that had to be estimated to calculate the final statistic. And in this particular case, we had to calculate a mean for y and a mean for x. So the corresponding degrees of freedom here is sample size minus 2. And then whenever we do statistical inference, we have to have the standard error of the statistic, right? You have a statistic, you see one value of the statistic, but you need the standard error, which is the standard deviation of that statistic over many, many, many different samples. Basically, it's standard deviation. And the standard error for the population, do statistical inference with the population correlation, if you assume the null hypothesis that the population correlation is 0, there's the standard error, 1 minus the correlation squared, sample's correlation squared divided by its degree of freedom, and then the square root of. And so then we base the hypothesis test on how far is the sample statistic from 0, the null hypothesis, divided by the estimated standard error. Again, the t-statistic is always how many estimated standard errors is something from the null value. And then the 95% confidence interval will be the sample statistic plus or minus the t cutoff of around 2 times the standard error. In other words, are we more than about 2 standard errors away from 0? If we are, then we say an unlikely event occurred because the probability is less than 5% that it would have occurred. So now that we have some of the basic concepts down, let's take a look at the actual output. And the output here comes from the correlation function, which just gives you the text output, the statistical analysis per se, or the scatterplot function, which will give you the same text output, but also give you the scatterplot. And here then we get the information of how many values are missing. In this case, there's 10 values that are nothing's missing, so there's no rows of data deleted. If any value is missing for either of the two variables, that row of data then is necessarily deleted because you need both values to calculate the correlation coefficient. We have something called the sample covariance, which we don't need to worry about right now. Then we also have the primary correlation coefficient, which here is 0.715. Now that's a long ways from 0, so we would generally expect, except for very, very small sample sizes, that we would generally expect the thing will be significant. That is to say that with such a large sample correlation, we generally expect to find that the population correlation coefficient is presumed not to be 0 then. And that's in fact what happens here. We get a t-value of 2.892. So the correlation coefficient of 0.715 is almost 3 standard errors away from 0. That gives us a p-value of 0.02, which is less than 0.05. So we conclude an unlikely event occurred if we assume the null hypothesis. So let's not assume the null hypothesis. Let's reject it and presume then that the two variables, height and weight, are related. Now notice that there's a very, very strong correlation, sample correlation of 0.715. But the p-value is 0.02. It's not 0.00000, it's 0.02. It's under 0.05, but not so much under, or it could be. And the reason for that is because the sample size is so small. So for such a small sample size, we need a very large sample correlation coefficient to be able to reject a null hypothesis that there is no population correlation, no relationship between the variables. And then we have the confidence interval, and you can see how wide that confidence interval is, from 0.16 to 0.93. And the reason why the confidence interval is so wide is because the sample size is so small. So we're saying that in this particular sample, we got a correlation of 0.72, but in the population, it could be anywhere from 0.16 to 0.93. Yes, it's not 0, but it still could be quite small as well. For such a small sample, we don't expect to get a lot of information, but we did get enough information from this particular sample to conclude that the population correlation coefficient is larger than 0, which means that the two variables, height and weight, are related to each other. So let's look at the interpretation of the results, which I more or less have said, but let's focus on it here. We have a statistical decision to rejecting a null hypothesis. The interpretation is that we detected a relationship, and we have a confidence interval, which does not include 0. So we conclude that there is a positive relationship because all the values in the confidence interval are larger than 0, which means these are all the plausible values of the population correlation coefficient. They're all larger than 0. But with 95% confidence, then, we conclude that the population correlation is somewhere between a weak value of 0.16 to a potentially very strong relationship of 0.93. So it still is true, as height increases on average, so does weight, but this small sample size doesn't allow us any much more precision than just a very general kind of statement here. So this then is our introduction to the correlation coefficient and the scatter plot, and not only talking about the statistics of the correlation, but also showing you a variety of different scatter plots so you can develop a little intuition for the size of the relationship and the corresponding scatter plot and correlation coefficient.